All right, welcome back. So we're going to be looking at using exponential functions to model particular word problems. And the example for exponential functions is population growth. And you actually can also use them for radioactive materials and exponential decay when you have a fractional value and calculating half-lives of particular elements, and use it for even things like carbon dating and calculating carbon-14 after thousands of years and things like that. But we're going to look at example 2 found on page 598 of your Red Algebra 2 textbook. So this is 598, example 2. And I'm not going to write down the problem here, neither should you, but I'll just quickly read the situation and maybe write down some facts as I do it. It says, during the 19th century, rabbits were brought to Australia. Since the rabbits had no natural enemies on that continent, their population increased rapidly. Suppose there were 65,000 rabbits in Australia in the year 1865, and there were 2,500,000 in the year 1867. Alright, so part A of this problem says, write an exponential equation that could be used to model the rabbit population in Australia. Write the equation in terms of the number of years elapsed since 1965. Alright, so we're going to be considering two variables, population and time. And t equals 0 corresponds to the year 1865. Alright, so years since 1865 would be our t, and that's going to be our exponent variable, alright, which recall was our x, and our y coordinate will be p, representing the population, alright, of rabbits at any given time since 1865. Alright, so if I want this to fit the model, y equals a times b to the x. Actually, let me replace the y and x with our new variables. So this would be p equals a times b to the t, right, where p was the population, t was the time since 1865. I've got a couple facts that I can work with. And recall that when we were sometimes you'd be able to find the equation of a line when given 2 points. That's a similar sort of situation we have here. I know that this situation is going to be representing an exponential function merely because it's population, and that's why I'm able to use this model. I'm going to plug in what I know and solve for what I don't. So the first thing, the population, I'll plug in, let's use this fact for starters. We'll plug in 65,000 for P. And we'll have a times b to the, and instead of 1865 for t, recall that I'm going to plug in 0 for t. So now perhaps I can solve for one of my variables. I do still have two variables left to solve for, but notice I actually don't have to worry about b just yet, because what is anything raised to the 0th power? That is going to be 1. So this is 65,000 equals a times 1. So a must equal 65,000. Alright, so that was our starting value of our population. Now, combining this and our other fact, I may be able to figure out the value of b. So once again, I'm going to plug it into the same exact model. I'm just plugging in this for my population. 1867, I'd have to consider years since 1865, so that's going to translate to t equals 2 for us, and I'll plug in 65,000 for a. So here we go. We've got 2,500,000 equals 65,000 times b, still is unknown to us, squared. Alright, so if I want to solve this equation for b, I could divide both sides by 65,000. And if I was doing this without a calculator, I'd recognize that I could cancel out some of these zeros. That's the same as 2,500 divided by 65. But fortunately, the work has already been done in the textbook for us. And I'm going to flip this equation around. B squared is equal to 38.46. And actually, that would be an approximate 38.46. If I was working in a calculator, I would have typed in these numbers divided. It would have given me its best approximation, so it would have actually gone out further than this. And perhaps you can see what the next step would be is going to be square rooting both sides. And yes, algebraically, I would have to consider both the positive and negative square roots here. But since this is an exponential model, we do not allow b to be negative, so we're only going to consider the positive values of b. So b is about, and on my calculator what I would have done is hit second square root, right, and then hit second answer. And it would have actually plugged in the full decimal approximation here, so I don't have to plug it back in myself, and we would get b is about approximately 6.20. Alright, so just like when we would find the equation of a line, y equals mx plus b, the values we were interested in were m and b, and I would always describe that as kind of being the DNA of your line, or the thing that makes it unique. We have found the two pieces of information that will make our exponential model unique. Alright, so our exponential model is y equals 65,000, being our starting value, multiplied by 6.20, which I suppose I could put in parentheses, 6.20, to the value of t. I want to leave t, and actually y is in reality p here, population. So this is going to be our population model. Now, part B of this problem says estimate the Australian rabbit population in 1872. So this was all part A. So part B shouldn't take as much room, but what I could do is, let's see, it's interested in 1872. So how could I find the appropriate t value for 1872? Well, I could actually just subtract 1865, and I believe that is, let's see, 7 years, so t equals 7 is what I have here. So what I'm going to do is just plug 7 in for t and evaluate for p, and that looks like all calculator work if I've ever seen it. So p is equal to 65,000 times 6.20 to the 7th. The way you would plug this into a calculator is 6.20, and you'd probably hit the little, it's called a caret. I always call them mountains because I think they look more like mountains than carrots. And then 7. Some calculators also have the y to the x button. Alright, so either of those buttons is what you'd do there. So 6.20 to the 7th power, and then multiply your answer by 65,000, and we would get the population is approximately 22,890,495,000, which is extremely large. And obviously, this and any mathematical model is usually going to have some sort of real-world limitations. We wouldn't necessarily expect the population to continue on in this infinite pattern forever, because there's going to be limitations such as food and area to live. Right? There'd be all sorts of constraints where we wouldn't necessarily expect us to be able to extrapolate. So I would doubt that the population actually was 22 billion at that point, but that's the sort of situation that a game warden would even consider in managing a wildlife population, is, you know, start figuring out, all right, how many hunting tags do we need to give out each year to try to manage this population based off of our, you know, square kilometers or whatever limitations we have. All right, so that's a classic population problem using our exponential functions. All right, see you next example.